So I'm going to continue to work through example 2, part D. I had mentioned that we need to find n in this question. So we need to find how many terms of the Taylor series centered at c is equals to 1 are needed to approximate ln 1.3 so that the error is less than. So we need to find n. And I explained how we came up with this formula for the error term. And I mentioned that we need to find the expression for the nth plus 1 derivative, all right? So we need to find the expression for this guy, all right? So we need to find that so that we can plug it into the error term and then use that to find n for the conditions given in this question. So what I'm going to do is I'll go back to the pattern of derivatives here, and I've just highlighted from the first derivative to the sixth derivative. I've highlighted the derivatives. So this is at n is equals to 1, at n is equals to 2, n is equals to 3, n is equals to 4, and n is equals to 5. All right. So if we have this, how can we be able to come up with a pattern? Let's start first of all with the denominator. Let's start with the easy one. So the denominator is just, we have x to the power 1, x to the power 2, x to the power 3. So that will just be x to the power n. Will that make sense? Yeah? X to the power n for the nth derivative. And then we can go to these numbers. This one's here. So you have 2. That's actually 2 factorial. That is 3 factorial. That's 4 factorial. That's 5 factorial. All right. So if you notice, that is 2 factorial. That is 2 factorial. For 3, we have 2 factorial. Here we have 3 factorial. All right. Here we have 5 factorial. Yeah. Sorry, 4 factorial, not 5 factorial. That's 4 factorial. All right. Here we have 5 factorial. All right. When n is equals to 6. So here we can say that this is n minus 1 factorial. All right. So that will be n. This is factorial, not 51. N minus 1 factorial. Now, the powers of -1, here the first term is positive, negative, positive, negative. So we can just say -1 to the power n plus 1. All right. So that if you plug in 1, then you'll have -1 squared, which makes it positive. When I have 2, -1 to the power 3, which is -1, and so on and so forth. All right. So this will be our nth derivative for this function. So what you're going to do is to go back down here and say that our n plus 1 derivative, so this will be equal to the nth derivative will be equal to what we've just found up here. All right. That one, -1 to the power n plus 1. All right. So I'm just going to copy it here. So -1 to the power n plus 1, n minus 1 factorial over x to the power n. Which means that the nth plus 1 derivative, hence f plus 1, derivative will be we are just going to plug n plus 1 in place of n, create more space. Make it more clear. N plus 1 x. So that will be negative 1 to power n plus 1 plus 1, and then n plus 1 minus 1 factorial over x to power n plus 1. All right. So what I've done is just to replace n plus 1, all right, in place of n, if you notice that. All right. So what I'll end up with is this will be equal to negative 1 to power n plus 2 multiplied by n factorial over x to power n plus 1. So this is my f n plus 1 x, n plus 1 derivative of this function. All right. Now that I have that, I can be able to write an expression so for the n plus 1 derivative at z. All right. So the n plus 1 derivative at z will be equal to negative 1 to power n plus 2 n factorial over z to power n plus 1. Okay. And then what I'm going to do is to replace this formula into the error term. So in place of this guy here, all right, I'm going to replace that derivative that we've just written down there. So my error term will now be equal to, so r will be equal to the absolute value, because remember here we want the magnitude of this error, negative 1 to power n plus 2 n factorial over z to power n plus 1 multiplied by what did we have up here? 0.3 to power n plus 1 over all this over n plus 1 factorial. Okay. We can simplify this. In fact, I'm just going to rewrite this expression. This can be simplified as the absolute value of all right, negative 1 to power. Now we don't have to write negative 1 again, because this is, absolute value also. So we can ignore that. Let me just write this. This can be ignored. Because of the absolute value signs. So what we'll end up with is something like this. N factorial multiplied by 0.3 to power n plus 1 over n plus 1 factorial multiplied by z to power n plus 1. All right. So we can simplify that expression that way, which can be even simplified further, because we know that this is same as n factorial over n plus 1 multiplied by n factorial. And here we have 0.3 to power n plus 1. And here we have multiplied by z to power n plus 1. All right. Now what happens is these guys will cancel. So my expression will become this will be equal to the absolute value of 0.3 to power n plus 1 over n plus 1 multiplied by z to power n plus 1. All right. Now we have to think about here, z is between 1 and 1.3. All right. So because z is between 1 and 1.3, remember this is centered at 1. That's why I'm saying that. All right. So the fact that z is between 1 and 1.3, and by inspection, by looking at this, we will have maximum error if z is equals to 1. Because if z is 1.3, we won't have maximum magnitude of error. Okay, so let me just write that statement here. Because z is between 1 and 1.3, by inspection, the magnitude of error will be larger or maximum if z is equals to 1. Okay, so we'll have maximum magnitude on the magnitude that will be larger if z is equals to 1. Anyway, if I plug that, so z is equals to 1. All right, I'm just gonna highlight that important things. So if I plug that into the error term here, then that will mean that our error term will simplify to 0.3 to power n plus 1 over just n plus 1. Okay, now but we want to find the value of n such that, back to the question, how many terms of the Taylor series standard are needed to approximate this so that the error is less than that, right? So the error, so that the error is less than that. So what we have to do is we have to form an inequality here and use our graphing calculator to kind of find out what it is. So the error is less than, so back here, okay. So we need to find n such that this is less than 1 times 10 to power negative 6. All right, 1 times 10 to power negative 6. That's what we have in the question. All right, so we are going to use GDCs. So use GDC, and I'm going to show you how to do that. So if you go onto your GDC, you can go onto y is equals to and just plug in this expression 0.3 2 power x plus 1 over x plus 1. Um, so, and then go to y is equals to, sorry, go to the table. So go to the table, and we want to investigate what will be the value of n such that the error is less than 1 times 10 to the power negative 6. So that will be, let's keep on going. No, that's not less than, that's not less than. Um, so less than, so that's 2 times 10 to the power negative 6. So the first value whereby, the error will be less than 1 times 10 to the power negative 6 is 9. All right, from here, from the calculator. So that will be 9. So which means n is equals to 9.